Imagine, just for a moment, stepping into the greatest crime scene in existence. We aren't talking about a single room, or a city block, or even a planet. We are talking about a scene that stretches across billions of light years. Today, we're taking on the ultimate cold case, the very origins of our universe. We are going to adopt the mindset of a cosmic detective, and together, we're going to hunt down the actual physical footprints of creation itself. Right out of the gate, we run into a pretty massive paradox, right? You might be wondering, how can scientists be so sure the universe even had a beginning, especially when we can't just build a giant time machine, travel back billions of years, and watch it happen? Well, the secret is that the universe isn't just a static, boring vault of empty space with rocks and gas floating around in the dark. It's an incredibly active, living, evolving system. And just like any system in motion, it changes. Because it changes, it leaves behind a trail of undeniable clues, footprints of its own history, just waiting for us to dust for prints and decode the story. But before we start pinning clues to our corkboard, we need to bust a major myth. When you hear the words Big Bang, I'd bet almost anything your brain instantly pictures a giant firecracker exploding in the pitch black, sending cosmic debris flying out into some pre-existing empty void. Honestly, scratch that entirely. The reality is so much more elegant and, frankly, a bit mind-bending. The Big Bang was not an explosion inside of space. It was the rapid expansion of space itself. Okay, let's put this into perspective so it actually makes sense. Think about baking a loaf of raisin bread. When you put the dough in the oven, it heats up and it rises. As that dough expands, the raisins inside don't suddenly shoot outward from the center of the loaf. No, the actual dough between the raisins stretches. Because the dough is stretching, every single raisin watches all the other raisins move further and further away. Our universe is exactly like that rising dough. Galaxies aren't flying through space like shrapnel. The fundamental fabric of space between them is what's literally stretching out. Every good detective needs hard evidence, so let's log our very first clue, redshift. When we look out at distant galaxies, the light they shine toward us is stretched out. It gets pulled toward the red end of the visual spectrum. Think about how a police siren drops in pitch as the car speeds away from you down the street. It's the exact same principle, but with light instead of sound. This stretched red and light is our smoking gun. It proves, without a shadow of a doubt, that the space the light is traveling through is actively expanding. So let's follow the logic. What happens if we hit rewind on the cosmic movie tape? It's pretty straightforward, but the implications are staggering. If all the galaxies are moving apart from each other today, then if we rewind the tape to yesterday, they had to be closer together. Rewind a million years? Closer still. If you keep rewinding that tape all the way back, the entire universe, everything we see today, must have been squeezed into an unimaginably dense, incredibly compact state. Now, when you cram all the matter and energy of the entire cosmos into a microscopic space, the normal rules of physics just kind of melt away. Extreme density creates extreme heat. But we aren't talking about literal fire burning in an empty room. Imagine the most packed, chaotic, high-energy dance floor you can possibly think of, and then multiply that by infinity. The early universe was a blinding, highly compressed crucible of raw, churning, chaotic energy. Which brings us to our second massive clue. If the cosmos used to be that intense, that incredibly crowded, and that unimaginably hot, it couldn't have just vanished without a trace, right? It had to leave a thermal fingerprint, and boy, did it ever. We call it the cosmic microwave background. It is a faint, invisible glow of radiation that we can detect coming from literally every single direction in the sky. It is the cooled, fading thermal afterglow of our universe's fiery youth. But let's look a little closer at that ancient glow, because the investigation goes deeper. When we measure that cosmic background radiation with ultra-precise instruments, we find our third clue. It isn't perfectly smooth. There are microscopic, tiny variations in the temperature. And honestly, we are incredibly lucky that's the case. If that early cosmic soup had been perfectly uniformly smooth, it would have stayed that way forever. We would have ended up with a blank, featureless void. Those tiny, microscopic lumps, they were absolutely vital. They were the seeds of everything. So, what did those tiny temperature bumps actually do? Well, they represented areas where the universe was just a tiny bit denser. And over billions of years, gravity stepped in. Think of gravity as an invisible, incredibly patient sculptor. It started pulling more and more matter into those slightly denser pockets. Over eons, it amplified those microscopic ripples, slowly gathering raw, swirling cosmic gas into the massive, sprawling, glowing networks of stars and galaxies that we explore today. Let's step back for a second and look at our completed cosmic crime board. It's honestly beautiful how it all comes together. We have 3 totally distinct, independent clues converging on one unified story. The redshift of distant galaxies proves that space is expanding. The cosmic microwave background proves that the universe was once a blazing furnace. And those tiny temperature variations explain exactly how we got complex structures instead of just a whole lot of nothing. It's a mathematically sound, airtight case. And all of this evidence highlights something really important. The Big Bang was not a single stopwatch moment. It wasn't a sudden flash of creation that was over in a split second. It was, and actually still is, a continuous, evolving, majestic process. From that initial hot, dense expansion, the universe steadily cooled. As it cooled, the very first atoms were finally able to stabilize. Thousands of years passed, gas clouds formed. Millions of years later, gravity squeezed those clouds until the first stars ignited. But as any seasoned detective will tell you, solving one mystery almost always uncovers another. The case file is never truly closed. If the universe has been expanding and cooling from this incredibly dense state, well, what caused that expansion to start in the first place? And what, if anything, existed before that absolute earliest moment? These are the profound, wide-open mysteries where our current maps of physics start to tear at the edges. But here's the thing, not having all the answers right now isn't a failure. It's a frontier. Science follows the evidence precisely where it leads, and it's brave enough to honestly acknowledge exactly where the clues currently run out. The fact that we don't know what sparked the initial expansion doesn't invalidate the billions of years of cosmic history we have mapped out. It just means there's thrilling, uncharted territory waiting for the next generation of cosmic detectives to explore. So what's our final takeaway? To me, the truest magic of all this is that we don't actually need a time machine to understand our origins. The past isn't gone. It's literally stretched out in the light of receding galaxies. It's echoing in the faint static of empty space, and it's woven into the very fabric of the cosmos around us. We are reading the universe's incredible history through its present-day clues. We've tracked the footprints of creation this far, but as we stand on the edge of the unknown, you have to wonder, where will those footprints ultimately lead us next?